Hello and welcome to today's lesson, Wave Interference and Standing Waves. Wave interference and standing waves. When two or more waves act simultaneously on a medium, interference occurs. The principle of superposition states that when two or more waves pass through each other, the resulting disturbance will give a point at the medium in the medium that is found by adding the individual displacements of the wave that the wave would have caused. Note that the displacements below the rest position are considered negative, so in the troughs. There are two types of interference when two waves are superimposed: constructive interference and destructive interference. So in constructive interference, you have two troughs or two crests. This will result in a larger individual disturbance. So we have three different parts. We have our before, we have our during, and we have our after. So before A and B are traveling towards each other. When they meet in the middle, their amplitudes are added together. So you ended up with a wave with an amplitude double what A and B were. And then as they separate their energy, they go back to their regular size. In a destructive interference, the resulting displacement is smaller than the individual displacements. And this process occurs when a trough and a crest meet. So in before, A is a trough, B is a crest. They're traveling towards each other. When they meet, because they were the same amplitude, there's no wave at all. And then they will continue on at their same size. The two waves in the picture before are traveling towards each other. Draw a snapshot of the superposition of the waves and also what they look like after superposition. State whether constructive or deconstructive interference is happening. So if we look at our first example, we have a crest that is too high and a trough that is going down one. When they're going to end up meeting in the middle. When this happens, we are going to add the distances together, or the amplitudes together. So it will end up, because the crest is larger, it will add up still being a crest, but smaller than the original crest. As they continue on after each other, you will still have the trough and your crest moving away from each other. So this is a destructive. So it's a destructive interference. Okay, in our second example, we have this big trough, or big crest, meeting up with this little crest. Okay, as they meet, their interferences will add. Alrighty, so what's going to happen here is we're going to end up with a wave that goes up 2 over 1, up 1 over 1, down 1 over 1, down 2. So and that's just because as this little wave moves towards here, it's not really going to do anything until it gets to the middle here. And that's where it's going to bump things up. And then, of course, as they go on, you'll have your little 1 guy and your 3 guy traveling away from each other. So this is a constructive wave. Standing waves. In a one-dimensional medium, like a string or a spring, If the amplitude and wavelength are just right, a standing wave will be produced. For the purpose of this lesson, we will be imagining a string fixed at both ends, for example, a guitar string. A standing wave is actually an interference pattern consisting of both maximum constructive and destructive interferences. What happens is the medium near the multiple waves are created in one direction. This wave then reflects off the fixed end and travels back the way they came, but inverted. Meanwhile, waves are still being produced at the original end. These waves lengthen in opposite directions, interfering with each other. However, it is only considered a standing wave when the waves interfere in such a way that it appears as if the wave does not move along the string. The places with destructive interference are called nodes. Nodes are at the rest position. The place where with constructive interferences are called antinodes. Antinodes look like crests and troughs. If you change the frequency of the wave, you can alter the separation of the nodes. The following conditions must be met for standard standing waves to exist. There must be two waves of the same frequency. One or both must be a reflected wave. There must either be a whole or a half number of wavelengths in the pattern. For example, 2 lambda or 1.5 lambda, but not 1.9 or 3.25 lambda. The second point is because the end of the wave must be a node which cannot exist at any other wavelength other than a multiple of a 1/2 lambda. The number of nodes and antinodes as well as the length they are apart will be useful information to help us determine the wavelength. Alright, so some examples. What is the wavelength if the distance between a node and an antinode is 8.35 centimeters? So the first thing I'm going to do is I'm going to draw a diagram. Okay, so that's the first part of the wave, and then remember the standing wave kind of looks like this. Okay, so we have those right there are my nodes. And up at the top then are my antinodes. So this question is telling me that halfway between node and antinode is 8.35 centimeters. Okay, so we know that the distance between any two nodes or any two antinodes is 1/2 of the wavelength. Therefore, we've halved that again. So 1/4 of the wavelength is 8.35 centimeters. So I have to multiply both sides by 4 to get rid of the 4 there. So then my wavelength ends up being 33.4 centimeters. Okay, and then second example, what is the speed of the wave if the distance between two adjacent nodes is 12.5 centimeters and its frequency is 375 hertz? Okay, so we know that the distance between two antinodes is half of the wavelength. So then lambda ends up being 25 centimeters. We know that our velocity formula is velocity equals lambda f. Let's do what we always do, knowns and unknowns. So velocity is what we're looking for. Lambda is 25 centimeters, and the frequency is 375 hertz. So we can sub and solve now. V equals 25 times 375. Okay, so V ends up equaling 9,375 centimeters per second, which isn't a unit that we use, so let's convert this into meters. So I'll divide by 100. So the velocity equals 93.75 meters per second. The number of standing waves in a standing wave pattern can be found by subtracting 1 from the number of nodes and antinodes and by dividing number of nodes and dividing by 2. Likewise, the number of waves can be found by dividing the number of antinodes by 2. The wave generated at point A are reflected at point B to produce a standing wave shown. How many antinodes are there in the pattern? What is the wavelength produced in this pattern? Alright, so let's start by counting our antinodes. So we have 1, 2, 3, 4, 5, 6. So we have 6 antinodes altogether. Okay, so what is the wavelength produced by this pattern? So we can figure out what our lambda is by figuring out that it's the number of waves, or we can figure out the number of waves. So the number of waves equals the number of nodes, which is 6, divided by 2. So we get 3 lambda. 3 lambda, so 3 wavelengths equals 12 meters. So we're just going to divide by 3 on both sides, and our wavelength ends up being 4 meters. Alright, so that's the end of today's lesson. If you have any questions, please ask tomorrow in class. I hope you have a great night.